Thank you so much. Yeah, I actually feel a little bit intimidated by seeing all the cool stuff that you guys are doing, but hopefully I'll be able to provide some interesting stuff as well. Yeah, so we're Mathias Davids from Harvard Medical School, and we're a group working on various medical imaging technologies, including magnetic resonance imaging, which this talk will be about. So as most of you probably know, medical imaging modality is, MRI is a medical imaging modality employing non-ionizing EM radiation. So MRI is based on the excitation of particle spins and measuring the resulting spin signals to essentially form an image. And I'll especially be talking about one component of an MRI machine, which is the so-called gradient coil, which we need for the signal localization. And so this is one of these gradient coils. The goal of the gradient coil is essentially to create a linear field variation of the BZ component, shown here. So a linear variation of the BZ component along one spatial axis, because the spin signal corresponds to the field strength, and essentially by that we can localize the received signal through this linear field gradient. We have a total of 3 of these gradient coils in a typical MRI system, one for each spatial axis. And if we look at so in order for this gradient coil to produce this linear field, we actually need fairly high, I can show you here, fairly high field magnitudes outside of the imaging region. So this would be the imaging region, and this is outside. And these high field amplitudes really cause some trouble for us in medical imaging, because we obviously want to switch these field gradients very quickly in order to have a rapid field acquisition. But then, as per Faraday's law of induction, these rapidly switching magnetic fields induce strong electric fields in the human body, and these electric fields are proportional to the amplitude of the magnetic field, to the temporal rate of change, and to the size of the exposed body part. And these induced E fields can then interact with the peripheral nervous system, leading to unwanted action potentials, which are then felt as muscle contractions or touch perceptions. And these peripheral nerve stimulation effects really have become a fundamental limitation on what we can do in MRI. So these PNS effects can essentially render a large portion of the performance space of an MRI system unusable. So shown here, for example, is the what we typically look at in MRI is the achievable gradient strength. So that's essentially the steepness of the linear field gradient as a function of the rise time. So the time it takes to ramp up the field from 0 to the maximum field. And if we overlay to this essentially the region inaccessible due to PNS, we see that we lose up to 60% of our hardware performance, especially for short rise times, which we need for fast image acquisition. So despite this large impact, PNS is not really addressed during the coil design phase, and instead measured in stimulation studies after the coil construction phase. So there's really a lack of knowledge. And this is where we started to work. So we essentially developed a PNS modeling tool that kind of predicts these stimulation effects. First of all, to understand the basics behind it. So where, why, and when does PNS occur? We want to predict the sites of the activation and the thresholds. We want to compare different coil winding patterns during the design phase. Ideally perform PNS constrained coil design, which I'll show at the very end. Essentially analyze different mitigation strategies. And MFEM has been playing a very central role in our efforts to develop these PNS models. So to dive in a little bit, we developed these coupled electromagnetic neurodynamic simulations, which are first of all based on models of the conductive tissue. So we have these 2 body models with very high spatial resolution, 1 millimeter cube, and all these different tissue classes, of which there are between like 40 and 50 tissue classes, are labeled by the correct dielectric tissue properties, especially the conductivity. And part of these body models are very detailed nerve atlases. So essentially atlases of the peripheral nervous system in the body, including all these different branching patterns, and all the nerves are labeled by the axon diameter, which impacts the excitability. And we're also correctly modeling these different branching paths as the different kinks, or the way the branch kinks through the body, has a large impact on the excitability. And then the workflow essentially looks as follows. So we start with simulating the electric field induced in the body by a given coil winding pattern. You can already see where MFEM starts to become relevant in our workflow. And so once we have these E fields, we essentially superimpose the nerve atlas to the E field map. We project the electric field onto the nerve fiber path, integrate the result to get these electric potential changes along the nerve fiber direction. And then we feed this electric potential pattern to an electric circuit model of myelinated nerve fibers to decide when and where the nerve would fire an action potential. And this, for example, would be the output of the nerve model, which is shown here as the transmembrane potential along the nerve over the time course of in this case, sinusoidal current waveform. And so as we increase the waveform, we then see at some point that the nerve is forming action potentials, which are then running down the nerve. And we note this coil current waveform as a function of rise time as the PNS threshold. So above this amplitude, we expect nerve activation in the body. And we repeat this process for different rise times to sample these characteristic threshold curves. And this is really how an MRI gradient system is characterized in terms of PNS. So the smallest stimulating gradient amplitude as a function of the rise time. And just as a side note, there's also an alternative to this circuit model, which is a calibrated linear nerve model, which essentially just analyzes the spatial properties along these electric potential changes. And this is based on calibrated parameters for a given waveform. And the important thing, which will become relevant later on, is that this oracle metric is linear in the electric field, which again is becoming relevant later on. And so in this workflow, which again starts by, so first of all, B field simulation, then we have the electric field simulation, and then the from the electric fields extraction of the nerve activation thresholds. The critical point here really is the electric field simulation, which is where MFEM starts to come into play. And so we've, because these body models, as you can imagine, are very, very complex, probably not comparably complex to what we've seen so far, but by our standards, very complex. So we have roughly 80 million mesh cells per model, 1 millimeter cube mesh cells, up to 50 different tissue classes. And so we essentially developed our own electromagnetic field solver based on the MFEM library. And we solved a very standard problem, which is the Magneto-Quasi-Static Approximation. So essentially we start by pre-computing the magnetic vector potential from a given coil winding pattern. And then we solve for the electric scalar potential given a certain this magnetic vector potential. And from this electric scalar potential, we can then compute the electric field in the heterogeneous body. So we've really been making big use of the partitioning and large scale parallelization capabilities of MFEM. And this honestly has been a game changer to us. So we were able to, so initially these simulations using commercial software packages take hours to sometimes days. And using MFEM, we've been able to bring this down to something like 30 to 40 minutes, which is separated into this in an initialization phase of 35 minutes in which we assemble all the matrices, and then computing the right-hand side and the solve step takes something like 2 to 3 minutes. And again, this compares to up to 2 days using commercial software packages. And so, as you can imagine, this tool has been super helpful for us. And just to give you a quick idea, so for example, we use this tool in the design optimization phase of a new head gradient, which is essentially the most powerful head gradient in existence, with very high performance specs, so very high gradient strength, very high slew rates, and some other important design characteristics, challenging design characteristics. And what we've essentially been doing is, first of all, study different ways how to design these coils and their impact on PNS. So for example, shown here are 3 different strategies on how to design the shoulder cutouts. So essentially how to accommodate the shoulders in these very small coils. You can see the resulting projections of the electric field maps, and then the extracted PNS hotspots. So this is plotted as the PNS oracle, which is essentially the inverse of the threshold. So it's a little counterintuitive. So we want to maximize the threshold, which means that we can drive the gradient fast without stimulation. And then we typically look at the inverse thresholds, which we call the PNS oracle. And you can see how these different E-field maps essentially lead to different activation patterns in the body. And we use these simulations to essentially fine-tune the winding patterns in an attempt to maximize the worst case PNS threshold. And then we built the coil, we did some experimental studies, and we really saw very good agreement between the experimental and the predicted PNS thresholds, shown here for the two axis coils, X and Y axis, the simulated data in red, the experimental data in blue, and you can see very good agreement, not only in the thresholds itself, but also in the, we also compared the sites of activation reported by the subjects in the experimental studies to our predicted sites, and we really saw good agreements. For example, the nose, like activations in the forehead and nose for the x-axis, and then activation of the shoulder and the scapula for the y-axis coil. And we've not only validated the tool using this coil, but also up to like 12 to 15 different grading coils. So we've really gone through kind of an extensive validation phase. And again, this led to the most powerful head system in existence. And despite this working quite well, we've wanted to push things a little further, and this is where MFEM really became kind of critical for us, which is that kind of manually tweaking the winding pattern is a little suboptimal because it's first of all time consuming, and it also relies on intuition. So the designer needs to know, okay, if I shift this winding pattern or this wire, that's what's going to happen to the PNS thresholds. So we wanted to come up with a way to essentially let the computer pick the ideal winding pattern. So to turn this whole thing into numerical optimization. And this is really where things became more, let's say, challenging, because the field simulation really still is computationally expensive. So it takes like 40 minutes for one let's say, coil simulation. And this is simply too complex to include in a numerical optimization. And so what we've come up with is essentially bypassing this kind of complex simulation step using a Huygens PNS model. And so what this means is essentially that we encapsulated the whole body with a Huygens surface. We populated the Huygens surface with a lot of small magnetic basis functions. This can be dipoles or small coils. And this is roughly like 3,000 basis functions. And for each of these basis functions, we simulated the electric fields, and then we extracted the PNS responses, so linear PNS responses for each basis function. And you can already guess that this is a very, very complex and like computationally challenging thing, because we have like thousands of basis functions, with each basis function taking something like 40 minutes, which would be weeks in computation time. And this is where we really kind of use the flexibility of the MFEM library, which is that the kind of time-consuming initialization phase we only need to do once, because this initialization phase really just depends on the body model, but not on the coil pattern. So in the initialization phase, we only essentially pre-compute the fixed quantities, and then for each basis function, we only update the magnetic vector potential, we compute the right-hand side, and we then solve for the electric scalar potential. So this means that per basis function, we don't really need 40 minutes in computation time, but only 2 minutes, which adds up to 3 to 4 days in total computation time. And this, again, was only possible due to this like flexibility that we got out of the MFEM library. And this really means that instead of doing this repetitively, like repeated E-field simulations, we can essentially bypass this and simply project the magnetic fields onto the Huygens surface. And this is a step that takes a couple of seconds or even milliseconds. And once we have this basis vector, we can then project this further to a given nerve activation pattern. And again, this is a super simple workflow, does not require any further E-field simulations, but only this one projection step. And so this final Huygens model that we developed is essentially stored in like a P matrix, which links the interaction between all the basis functions on the Huygens surface to all nerves in the body. And it's importantly, it's body model and waveform specific. So we usually have a multiple of these P matrices. But the important thing is that we can essentially easily disseminate this tool. So we don't need, in order for people to use this tool, they don't need a powerful computing server. They just need MATLAB or Python to compute this projection step. And otherwise which can be done on a simple laptop. So they don't need this like $100,000 computing server, which we have been using. And again, this projection step is also very fast. And this Huygens approach really allowed us to do something very cool, which is incorporating nerve stimulation metrics in the winding optimization. And this is the last thing I want to touch up on. And to give you a very quick idea of what the coil design problem typically looks like. So essentially, we usually define a coil geometry on which we want to design the coil. We define so-called stream function bases on this coil geometry, which essentially model small circulating electric currents around a vertex. And then we pre-compute the field contribution of these small basis function in the imaging volume, so in the linear volume. We can then assemble a system matrix that links all the stream function bases to all the target points. And we then simply formulate the coil design as a constraint optimization problem. So we solve this basis set for a certain target field, which is, for example, a linear gradient field to get these winding patterns. And the cool thing is now with our Huygens approach and the let's say pre-computation that we've been doing using MFEM, that we can do the same pre-computation using nerve stimulation. So we can essentially pre-compute the PNS contribution for each of these basis functions. We get you can see how this impacts the distribution of nerve activation in the coil, and we can then include this as a constraint in the winding optimization. This has been like a big step for us. And just to give you a quick look on the results. So if we what we typically look at is essentially the PNS oracle is again the reciprocal threshold as a function of the coil inductance, and this is this kind of typical L-curve analysis. We can essentially see how, as we step by step enforce PNS improvements, you can see how the coil winding changes. And then if we pick something which does not look extremely crazy, so you can see in the beginning these winding coils, winding patterns are somewhat feasible, and at some point they become a little funky, I would say. But if we pick something feasible, this is something we could absolutely build. And this is a factor of 2 improvement in terms of PNS. So this is like a massive step in what we can do in MRI imaging. And at the moment, we're building these coils, doing some final testing, and see if this actually works in reality. And again, I briefly mentioned this. So this can really lift up the PNS threshold curves dramatically, and we're again finally assessing these coils, building prototypes, and doing some final testing. Last slide. So I think we only scratched the surface of what MFEM can do for us. We're definitely want to push things further. We've been working on non-conforming meshes to increase the spatial resolution. We want to eventually switch to tetrahedral meshes. So this result is a couple of years old, and back then I think I had nightmares for 2 weeks because generating these meshes is a pain. But we do want to revisit this, and we're also having other research activities, including cardiac and retinal stimulation, where these like MFEM is also becoming more and more relevant, especially because we're kind of facing the challenge of having non-isotropic conductivity in the body, which we eventually want to include in the. So quick summary. So yeah, these PNS modeling tools have been tremendously helpful for us, and we've already made successful uses of these tools, and there's more uses coming up in the near future. And the role of MFEM really has been tremendous for us because it allowed us to utilize Huygens principle, do these kind of time-consuming pre-computations, and essentially develop an AM solver tailored to the problem at hand. And I also want to use the chance to really give a big thanks to the entire MFEM team, first of all, but also to special thanks to Mark, Veselin, and Sanil for being so helpful during the development phase. So this has been tremendously helpful, super responsive, and I feel if we would have gotten the same amount of support from companies that charge $10,000 per license per year, I think we would all be living in a better world. So with that, big thanks to all my colleagues and collaborators and our funding sources, and of course, thanks to all of you for listening.